Hello, and welcome to the Weights and Queues module of the Microsoft Certified Master SQL Server online training. This training is not supposed to be a substitute for the broad experience and deep knowledge you'll need for this certification, but it will give you an idea of the breadth of material you're supposed to know and the depth to which you should know it. By way of a very quick introduction, my name is Paul Randal, and I've been an instructor of the MCM SQL certification since its inception as the Microsoft Internal Ranger program. I'm an expert in many aspects of SQL Server internals and usage. I spent 9 years on the SQL Server storage engine team, and now I spend my time teaching, consulting, and writing about SQL Server. You can read the rest of this intro slide for yourself. So in this short module, I'm going to discuss weights and queues. I'm going to explain the weights and queues methodology and why it's an incredibly useful thing to get to know and to be familiar with when you're doing performance troubleshooting. We'll look at the thread execution model and the three states, running, suspended, and runnable, and what those mean. And we'll look at how you can examine the weights, and we might talk a little bit about some of the different weights that you might see. So very often what I find is people will start to performance troubleshoot a system and they don't really have a clear idea of where to start looking. Now, SQL Server is written to keep track of all of the weights that occur inside it. So SQL Server knows exactly what's going on in terms of what resources are having to be weighted for, whether there's contention for the CPUs and so on. So using the list of the most obvious weights that are occurring on the system, you can then figure out which set of resources you should go and investigate. So SQL Server is keeping track of the weights, and the queues are the resources that SQL Server is waiting on. So whenever I'm going in to do any performance troubleshooting, one of the very first things I'll do is I will look at the weights that are occurring on the system to see a kind of very simple snapshot of what's going on in the system. So a weight occurs when a thread that's running decides it needs a resource, and so the resource has to become available. So by resource, there's a bunch of different things that could mean. So there's some examples I'm going to walk through. So the thread might decide that it has to take a lock on a particular page, a relational level lock, to protect something that's going on. So for instance, you might be using the read committed isolation level, and you're doing a select. So before a particular row can be read, there is going to be a share lock taken on that particular row. If you specified specifically to use page locks, then there might be a share lock taken on a page for it to read all the rows on that particular page. So that's going to show up if there's blocking occurring. So if something else is holding a lock that's preventing that thread from being able to get that particular lock, then that's going to show up as an LCK_M_S weight. In other words, a lock mode share weight. If a thread decides that it needs to read a new copy of a page, so it might decide to read a page from disk, the buffer pool is asked to provide a pointer to the area of memory, the 8K area of memory that has that page image in. If the page isn't already in the buffer pool, then the buffer pool has to go and issue an IO to read the data page from disk. So while the data page is being read from disk, the thread is suspended, and it's suspended waiting for what's called a page IO latch wait. And that could be for an exclusive latch, it could be for a share latch, where a latch is basically a lighter weight synchronization mechanism than a lock. So reading a page from disk that's not a data page, then the wait type will be an IO completion wait. And then, for instance, if you have a query that's running in parallel and the number of rows to be processed is divided up unevenly amongst the threads that are executing the parallel query, then you might find that you have what's called a CX packet wait. And CX packet waits are basically saying that the portions of the parallel query are not processing the same amount of data. So one finishes before the others, for instance, and it's having to wait for the other portions of the parallel query to continue executing. So while a resource is being waited for, the thread can't continue. So the thread gets suspended. Now, you can see the weights that are happening on the system through a variety of DMVs I'm going to talk about. You can also use Performance Dashboard in 2005, and you can use the data collector in 2008. So once you've figured out what the weights are, you then can go and look and see what the resources are, in other words, the queues. So this is the weights and queues methodology. So a queue is basically something that's stopping a resource from being available. So going through the kind of list that we had from the previous slide, if a thread is waiting for a particular lock and some other thread is already holding an incompatible lock, then that's the resource having to wait for, is that second thread to release its incompatible lock. Talking about query parallelism, so if one portion of the query finishes first and the other portions haven't yet finished, then it's going to be a CX packet wait. The resource that's being waited for, in other words the queue, is the rest of the parallel query to finish. If you're seeing SOS scheduler yield waits, that could be that there's contention for the CPU. There's so many threads running and the CPUs are having to the threads are essentially having to give up the CPU to allow other threads to continue running. That's another example of a resource. And then a very common one to be able to think about is an I/O subsystem, where the resource is waiting for a particular I/O to complete. Now, the resources, the queues that you're going to investigate, you're typically going to use other DMVs and also looking at perfmon counters, either using Performance Monitor itself or using the DMOS Performance Counters DMV to look at these particular perfmon counters. So let's have a look at how threads execute inside SQL Server. So there's three different states that a thread can be in. It can be running, which means it has a CPU and it's running right now on the CPU. It could be suspended, and there is a list of threads that are suspended waiting for particular resources. The list is completely unordered. It's just there's no guarantee that any one thread is going to be signaled that its resource is now available before anything else. And then there's the runnable queue, which is a FIFO queue, a first in first out queue of whenever a thread goes from suspended and is notified that that particular resource is available, it goes on the bottom of the runnable queue, and threads get pushed basically off the top of the runnable queue when the CPU is free and available for another thread to continue running. So taking this particular example here, if we move on, so say the thread that's currently running, SPID 60, requires to do an operation, and it's going to have to read a non-data page from disk. So it becomes suspended, and the resource that it's waiting for is an I/O completion to happen. So once it becomes suspended, the CPU is now free, and the thread that's at the top of the runnable queue can then transition to being running. So SPID 51 is going to transition from runnable into running. Now, as soon as SPID one of the SPIDs in the suspended list gets notified that its particular resource is available, it will change from being suspended. So there's SPID 56, for instance, there. SPID 56 is waiting on a CX packet, and as soon as SPID 56 is notified that its resource is available, it becomes runnable again and goes on the bottom of the runnable queue. So this is just showing the example of after thread 60 has become suspended, thread 56 has become runnable again, and 51 has been pushed from the top of the runnable queue onto the running state. This is just kind of finalizing that particular clockwise sequence of slides that we had there. So threads basically from the start of the query to the end, they go around this clockwise loop, going from running to suspended to runnable to running again. Now, in terms of wait times, the two different wait times that we have are the resource wait time and the signal wait time. So the OS wait stats DMV gives us the total wait time, and it gives us the signal wait time. We have to work out the resource wait time for ourselves by simple arithmetic. So the resource wait time is the time that the thread is basically sitting suspended, waiting for the resource to become available. The signal wait time is how long the thread spends on the runnable queue. Once it's been signaled that the resource is available, it gets put on the runnable queue, and then it's going to have to wait until it reaches the head of the runnable queue and then gets the CPU and becomes running again. So the total wait time is the amount of time that the thread spent on the waiting tasks queue being suspended, plus the signal wait time, the amount of time it spent on the runnable queue after the resource had become available and waiting to be actually running on the CPU again. So in terms of the DMVs that you can use to look at wait stats, the main one is sys.dmos wait stats. Now that gives you a server level look at all of the wait types, and it tells you how many waits there have been for that particular wait type since the wait stats were reset. Down at the bottom there you can see you can reset the wait stats. Very, very useful for perf troubleshooting to be able to make a change, reset the wait stats, and see whether you've actually changed the distribution of what waits are happening on the system. So you can see that the DMOS wait stats gives you the server level aggregation. It lists all the different wait types, how many times each one's been waited for, the total wait time for each type, the signal wait time, so you have to figure out the resource wait time. And you can put together a script that aggregates all this stuff together. In fact, there's an example that I'll show you in the demo of a script that does some aggregation on wait stats, and for instance this script will list them all in kind of percentages, what percentage of all the waits that are happening on a system are a certain type. Now the DMOS waiting tasks will show which particular tasks are waiting for something. So you could join that together with some of the sys.dmexec DMVs to be able to see the T-SQL that's running for a particular task and see what it's waiting on. You could even have a look at the query plan and see what it's particularly waiting on in that time frame. Another way of being able to look at the wait stats is using extended events. Now the DMVs, as I mentioned on the previous slide, give you a view of what's happening across the whole server. If you have a very busy server and you're trying to figure out what waits are happening for a single statement or a stored procedure, for instance, that can be incredibly hard. Now, because even if you reset the wait stats, everything else that's happening on the system is going to be generating waits, because waits happen all the time. Just because there are waits doesn't mean it's a particularly bad problem. So to be able to narrow down and capture just the waits that are occurring for a particular statement or batch, for instance, you can use extended events, and there's a wait info event that fires every time a wait starts and a wait stops, and you can use a filter to be able to capture just the wait info events for a particular connection to the server. And in fact, as it says on the slide there, if in the extended events module, the second part of the demo that I've recorded for the extended events module actually has that particular demo in it, showing you how to capture capture wait info just for a particular connection. So as I said, waits are always happening. Now, there are all kinds of different waits, and a bunch of them you can ignore because they're just background tasks that are doing things. And if you look in the demo code that accompanies this, you'll see the demo code actually filters out a whole bunch of different events because most of the time they are nothing that you can do anything about. So you're looking for waits that are actually showing you that there could be a problem. So for instance, considering lock waits. Now, we might see, say, 1,000 waits for a share lock. The kind of wait that occurs, though, is going to let us know if it's a problem or not. As it says there, if there were 10 million locks acquired over the course of, say, 8 hours, and those 1,000 waits were over the course of 8 hours, and each of these waits was only for, a fifth of a second, for instance, then is that really a big issue? No, I would say probably not. But if each of those 1,000 waits was for 50 seconds each, then that says that we've got some large-scale blocking problem, and I would want to go and investigate what was going on, figure out what thread was actually, what connection was actually having those locking issues, and go and do something about it. Now, one of the things that's very useful to do is take snapshots of the wait stats every so often, so you can do time series analysis and figure out whether there's a trend occurring. Maybe one particular type of wait is becoming more prevalent on the server, and that could indicate a problem that's starting to slowly occur. So here's some example weight types taken from, in fact this is taken from the end of the demo that I recorded for this session. And you can see that the script that I've put together is showing the weight types. It shows the cumulative weight in terms of seconds for that particular weight type, the cumulative resource weight, the cumulative signal weight, the number of weights that have occurred, and the percentage of all the weights that have occurred since the weight stats were last reset that are for that particular weight type. So on this particular system you can see that the buffer pool flush weight is the highest weight, and that's waiting for buffers to be written out of the buffer pool. Now we can also see some locking weights there. Now for instance, you can see down there the share mode lock weights. Let me just do this. The share mode lock weights here, okay, they're the total wait time 42 seconds, but there's been 1,559 waits. Now that says that each of those waits is very short, so I don't really care about those. But look at this. So there's these exclusive mode waits where the total wait time is 44 seconds, but there's only been 2 waits. So each of those waits was for 22 seconds. So that's something that I'm interested in. And also maybe up here as well, these intense share lock waits. Okay? The total wait time 138 seconds. There's only been 6 waits though, so each of those waits was 20 seconds. That's something that I'm interested in. So an example taken from a customer that I dealt with earlier in the year. Some of the details have been changed to anonymize the customer. Imagine a system that's storing a set of car sales information and kind of listings of cars that are for sale for a whole bunch of dealers across the entire United States. And there's this one site that's storing all of this information, and the system has all kinds of performance problems. So a lot of performance problems listed there. Okay, lots of non-clustered indexes on this one big table called listing that has all this information stored in it. There's a huge amount of I/O going on. Some of the queries are seeing blocking. The buffer pool has a low page life expectancy. So by looking at the weight information, we can see that there are a lot of the weights that are occurring. The major percentages are CX packet weights, which can say that there's parallelism going on that we might not want, SOS scheduler yield weights that can indicate some kind of CPU contention, write log weights which can possibly indicate I/O subsystem problems with the log. Now I say possibly because on a very heavily loaded system with lots of concurrent connections, the write log weight isn't just necessarily showing the weight at the I/O subsystem level. It could also be showing weights for a spin lock inside the log management system. So to really dig in and prove that the I/O subsystem for the log is an issue, you might have to use the sys.dmio virtual file stats to see the actual I/O weights that are occurring on the log drive. And then page I/O latch weights are saying that the system is waiting for data pages to be read from disk. So one of the things that this might say to me is all of these things together says that there could be, apart from the write log and the SOS scheduler yield, the page I/O latch weights and the CX packet weights could say that there's large parallel table scans going on based on experience from what I've seen on other systems. Now, from digging in further, in other words, taking the weights and then looking at the queues, looking at perfmon counters, looking at the various DMVs and so on, and analyzing what query plans are occurring on the system, what it turned out to be was that there are many queries that are occurring that aren't using the non-clustered indexes that are defined on this big table. And so lots of these queries are actually doing table scans. So there's a lot of concurrent table scanning going on, which is contributing to these weights. So by changing some of the queries, by changing some of the non-clustered indexes, we were able to remove a lot of this weight activity and speed the system up. Now, one of the things you can sometimes try to do with CX packet weights is consider turning off parallelism. So setting the max DOP setting for the server to 1. Now, that can be a very useful thing, but you need to test it to make sure that you don't end up actually slowing things down. Now, the demo that accompanies this module, I've got a couple of demos that are going to show a system that has performance problems, looking at the weights and queues, and then making a tweak to the way the system is set up to show how that changes the weights that are occurring on the system. And then I'm going to show you some blocking that's occurring and how you can see that with weights and queues as well. So just to summarize, what we've looked at here is what the weights and queues methodology is, so the definition of weights, the definition of queues. We looked at thread execution and how threads move from running to suspended when they need to wait for a resource. When they get signaled that the resource is available, they get made runnable, they go on the bottom of the runnable queue, and eventually they bubble up through the runnable queue and they get back to running again. And then we discussed some of the different mechanisms for looking at weights and some of the actual weights themselves. So as always, go out to sqlskills.com/mcm.asp for a lot of additional information, links to blog posts and white papers and so on, that's going to help you studying for this particular portion of the MCM certification. Thank you.